the big fancy thing that makes four-unit integration is really integration by parts. Okay, a lot flows out from that, and you can sort of feel really, really powerful. Like, I know what integration by parts is. And you mention the name, people are like, integration what? And you're like, yes, let me show you this magic. And when you actually use the rule, it really does look like magic. If you don't write down the formula, people will look at it and say, where on earth did you get any of that from, right? Now, the thing is, it's so powerful. It leads to some, because it opens up so many avenues for things you can integrate, right? It actually makes the kinds of problems you encounter so difficult that actually it spawns whole other sub-methods underneath it to deal with that new category of harder problems that you can now address, okay? Which is what today's lesson is about. So therefore, to make sense of this, let's go back to what integration by parts is. By now, hopefully, we have the formula for integration by parts in our head. Where do we start with? Integral of u dv, right? So these are the two things that you have to choose, right? What's on the right-hand side? uv, good, minus the corresponding integral, right? Okay, good. Now, what I want to draw to your attention as you look at this is that because integration by parts gets an integral by way of another integral, right? Sometimes this integral over here, you have noticed, doesn't always just fall out. Sometimes it's still something you have to integrate by parts again, okay? So I just very quickly want to draw your mind back to an example you have already done, which I think was x squared e to the x. Okay, x squared e to the x. Now, let's quickly rehearse. What's this going to be equal to? What would you choose for u, and what would you choose for dv? It's not too hard, being that you've got x squared and e to the x. Clearly one is easier to integrate and one is going to be more beneficial to you to differentiate. Which one's which? U is going to be x squared, isn't it? Because when you get your du over here, the power is going to reduce, right? And correspondingly, e to the x is, well, you don't really need to do anything to integrate it, do you? Okay? But once you've done this, right, when you execute this line here, okay, watch what happens. Do you remember? There's uv, so no problems, okay? But then when you do this part, there's a factor of 2. I'm not going to worry about it inside the integral. You're going to get this. Okay? Now we've been doing this topic long enough that you recognize x e to the x. You're like, oh, I can do something with this. And at the very least, it's better than what I started with, right? So then you look at this thing, and you go integration by parts again, right? I wonder if you could do this part. Could you do it in your head yet? Is it simple enough that we could? Again, the choice of u and dv is quite obvious, isn't it, right? So when I choose my u and my v, which is slightly different here, what will uv be? It's going to be x e to the x, isn't it? Okay. When you've got your v du, what's going to happen? Well, because u is now x, right? Your du will just be 1. So you get this. Okay. So now we have reached a point where I can deal with this. That's just regular, even 2-unit integration. Okay. So no problem. I can bring this back to bear on my original question. Okay. This is going to be x squared e to the x minus x e to the x minus e to the x, and because I've integrated everything, I can whack a constant on the end of it. Okay. Now here's the thing, right? You go through this process, hopefully you can see there is a pattern going on here, right? For instance, the fact that we had to do integration by parts here, and what we had to integrate by parts again, you can see it's clearly in the same family as what I started with in the first place, right? I started with x squared e to the x, and then what I had to integrate again by parts was x e to the x. It's clearly not a coincidence, right? Mathematicians, we're always trying to see, things that aren't coincidences are patterns. So we should be able to take advantage of that and express that in some kind of general way, not just with 2s and 1s or 3s and 2s or whatever, okay? Can we get this in a broad way that can, I don't have to have specific numbers in here, okay? So let's consider, and if you haven't started writing this because you're like, oh, we did this before, you should write this one down, okay? Let's consider where it's not x squared, but some arbitrary value of x to the, well, I guess we might call it m. Okay. Now, in order to make this easier to work with, you've seen before, sometimes it helps to just call your integral I, right? But I'm going to have different integrals flying around, as you can see here, and I want to be able to distinguish between them, okay? So I'm going to define I subscript m as whichever power of x I'm after, okay? So we'll call this one x and e to the x, okay? Now, we were looking at, the case we looked at here was I2, wasn't it? Okay? And you can see as well that I1 appears, where does it appear? Right there, okay? So you can see I'm going to have different i's floating around, but I'm talking in abstract terms, so it's all n's. I don't actually know what these numbers are, okay? But I can still handle them in just the same way, right? So watch. If I were to integrate this by parts, okay, I would choose, well, I'd still make the same choices for u and dv, wouldn't I? Right? You'd still put your x to the power of whatever in here, which would give you a du on dx of nx n to the minus 1. Yep. You still chosen this as e to the x for the same reason we did before. So there's your, whoops, sorry. There's your v. Okay. Good. Let's move into this now and actually integrate this. So here's my uv, x, and e dx. Now my v du, I'm going to take that n out the front because again, just like in this case, it's a constant. I don't really need to worry about it. I'm going to have minus n integral, okay, v du. Whoops. Yeah, that's right. No, I've done that. Okay, now this is what we expected before, right? We had n as 2, so there's 2, and the n minus 1 is 1. There you go. So far, so good. Okay. But at this point, because I've defined I as this, right? This is another kind of I, isn't it? Which one is it? It's I, but the only thing that's affected is the power, which is n minus 1. So I've got n lots of I, n minus 1. I'll look at this for a second with me, okay? What is this? This is a very, very important line here, okay? What you've got is that thing which you hate in a dictionary, right? You're like, what's the meaning of, I don't know, what's a funny word? Or a simple word even. What's the meaning of playful? It's like, see play, and then you go to play, and it's like the act of being playful. You're like, that's not helpful, right? You've got something defined in terms of itself, okay? Now this is such a crucial idea. It has its own word. It's called recursion, right? And you can hear the root word in there, right? When something is in English, a recurring motif, right? It's the thing which happens around and around in circles, okay? Now it's not quite, I to the n in terms of I to the n over here. We saw some examples like that. I think we did, let's see. When we did e to the x sine x, I think, okay? When you evaluated this, you actually got another I over on the right-hand side and you had to bring it over, okay? Because minus I, right? But here you've got I to the n and some previous version of I, right? But we've been used to this kind of thing before, right? Like way back in year 7, we learned about different kinds of sequences, and some of them are best described recursively. What's the big example? Think about it. There's one sequence which you're very, very, very familiar with, but there's actually, there are non-recursive definitions for it, but the recursive definition makes sense the most. Does anyone recognize it? What's this series? This is the Fibonacci series, right? What's the definition of the Fibonacci series? If I want some arbitrary term, an nth term, for instance, the nth Fibonacci term, how do you calculate it? You have to add up the two previous terms, don't you? If I wanted this one, for instance, I would take these two, right? If I wanted this one, I would take, you get the idea, okay? So how would I write this? I would write it as the previous one plus the one before that, okay? This, just like this, is a recursive definition, okay? It just so happens that there's a non-recursive definition for the Fibonacci series, but it's really weird. It's got like, even though it's all integers, it's all whole numbers, somehow You've got weird numbers like this, irrational numbers that creep into the non-recursive definition for this. It's a golden ratio, by the way. Anyway, so you're familiar with this idea of recursion. You just haven't met it for a while, and you certainly haven't seen it in the context of integrals. Okay, but it's really, really useful. Let's see what happens. I had the case of I2 here, right? And because the n was quite small, you could deal with it in this way, all right? And it wouldn't be too difficult. But if I increase the power, right, you're going to have to integrate and then integrate and then integrate so many times, it can get quite confusing, right? So we're going to use this idea here, and by the way, this line here, this line, rather than calling it a recursive definition, they call it the recurrence relation. Okay, it's the same idea as with Fibonacci, they just give it a fancy name. Okay, this is the recurrence relation for xn e to the x. Okay, now we can use this directly. Okay, for instance, if I asked you, I'm just going to increase the power by 1 because I just want to demonstrate the concept. Okay, if I asked you to integrate x, let's just push it up to x cubed. Okay, I could go through this process and it would work okay, right? But it will be faster and more efficient if I use this and take advantage of it, okay? So if I go with this definition, what is this? This is I3, isn't it? That's the case that I'm looking at, that's the power, right? So I'm gonna go straight to this line, okay? This is really kind of integration by parts on steroids, really. It's sort of taking this part here and automating it, if you like. Okay. So what is I3? By definition, okay, you're gonna get back x cubed e to the x. There's my x to the n for this chosen value of n. Right? And then what happens over here? Well, I'll get 3 lots of I2. Is that okay? That's the I n minus 1. Okay. Well, I2 I can define in terms of I1, right? What's this going to be? This is going to be x, now my n is 2, x squared e to the x, minus, what's my n now? 2, I1. Okay? So can you see what I mean? That this here is doing what we were doing over here, but just automating the actual process of integration. Okay. All right, I'll go again. It's 3 x squared e to the x. Okay, what's I1? Well, 2 lots of x to the 1 e to the x minus, what's I in this case? Sorry, n is just 1, so I've got I. Now, n minus 1 is 0 in this case. Now just pause for a second, okay? What have we reached at this point? Does this look familiar? It should, because we did it about 5 minutes ago, right? It corresponds to this line, okay? So I0 is this. Let me highlight that. Can you see why? This I0 corresponds to this line, exactly. Why is that? Well, because I0 is x to the power of 0, e to the x, which is just e to the x, okay? Now at this point, I can stop. I don't need to use this recurrence relation anymore because I know what this integral is. I can just calculate it, okay? So I would say that's x cubed e to the x minus 3 lots of this minus 2 lots of this. The integral of e to the x is just e to the x, as we already calculated. That was my very last integral, so I better slap a constant on there. Okay. Now that's correct. Bit messy, but so let's just tidy it up. I see a common factor of 4 terms. They've all got e to the x in them, don't they? Okay. What have I got out the front? I've got an x cubed there. I've got minus 3x squared here. I've got negative 3, negative 2, that's plus 6x here. And then I've got negative, 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 minus 6 there, plus my constant. Okay. Does that match up? There you go. Okay. So you can see the way it worked, right? The recursion here, it makes this thing sort of long over here, which corresponds to my working out sort of expanding as I'm trying to resolve these integrals that I don't know what they are. But once you do this, once you integrate once, you're doing the same kind of integration repeatedly, okay? So that's why you don't need to do it all over again like we did here. You can take advantage of the pattern. Make sense?